Hi, my name is Ray Tao from Hong Kong University of Science and Technology. Today, I'm going to introduce my paper, A Theory of Contraction Updating. The paper mainly deals with belief updating when there is ambiguity. Ambiguity refers to the situation when there is no objective probability. A famous example is provided by Ellsberg, where he considers an urn with 100 balls. Each ball in the urn is either red or blue, but we don't know the precise proportion of red balls in the urn. So if we pick a ball from the urn, then the probability of getting a red ball is unknown. There is ambiguity. There are a lot of theories trying to accommodate situations like this, and one of the most successful models is proposed by Gilbert and Schmidt-Medler, the max-min expected utility model. In this model, ambiguity is captured by multiple priors. For instance, we might not be able to tell what is the proportion of the red balls in the urn, but we might believe that the proportion of red balls in the urn ranges from 1/4 to 3/4. A natural question arises in such situations. If a decision maker has multiple priors, then how would she revise her beliefs when there is new information? And this paper precisely deals with such problem. Let me give you a simple motivating example. Imagine that there is an investor who is deciding whether to buy a stock or not. The investor believes the price of the stock would either go up or down, both with probability half. The investor can consult an expert who perfectly knows the price trend of the stock. However, the expert might lie, and the probability for the expert to lie is unknown, just like we don't know the probability of getting a red ball. So equivalently, you can imagine that here, if we get a red ball from the urn, then the expert tells the truth, and if we get a blue ball from the urn, then the expert tells the lie. So if the suggestion of the expert is that the price will go up, how will this change the investor's belief? A simple analysis indicates that the investor should maintain her original belief. First, the suggestion of the expert is actually not informative because it can be interpreted in two contradicting ways depending on whether the expert is telling the truth or not. Second, there's no prior ambiguity of the investor, so the information does not help to resolve the ambiguity of the investor. So, the investor should just ignore the suggestion of the expert and maintain her original belief. However, the two benchmark rules, four-Bayesian rule and the maximum likelihood rule, predict differently from our analysis. With the two rules, the investor's belief would be dilated by the suggestion of the expert. That is, with the suggestion, the investor would revise her belief such that she believes that price going up to have multiple probabilities. For example, ranges from 1/4 to 3/4. So both four-Bayesian and maximum likelihood might lead to an increase of ambiguity of the decision maker. This hypothesis is tested by Shishkin and Ultralaver, and they find that for ambiguity-averse subjects, their belief is not dilated by such information. And this highlights the importance of a new updating rule that allows for no dilation. Let me formally present the updating rule in this paper, the contraction rule. Let S be the state space, which is assumed to be finite throughout this presentation. The set of priors is given by P, which is assumed to be convex and closed. The realized event is a subset E. I need to define two things. The first is the contraction measure mu P. It assigns each state of the world its maximal probability. And because the prior set has multiple priors, the contraction measure might not be a probability measure. For each measure pi and event E, we define pi restricted on E as a new measure that equal to pi on E and assigns measure 0 to the complement of E. So pi restricted on E is not the conditional probability of pi on E. The contraction posterior set is given by QCPE, where here C means the contraction rule, P is the prior set, and E is the realized event. It is given by the following. There are two cases. In the first case, the contraction measure assigns E a measure that is less than or equal to 1. We interpret this case as the realized event has small ambiguity, and because of that, its realization completely resolves the decision maker's ambiguity, and the posterior set is a singleton. The posterior Q star maintains the maximal likelihoods of each state of the world. And equivalently, you can imagine that Q is the normalization of the contraction measure on E. In the second case, the contraction measure assigns the event E a measure that is strictly larger than 1. We interpret this case as the realized event has large ambiguity, and because of that, the posterior set contains multiple posteriors. And in particular, every prior P is updated to some posterior phi. Let me explain what this phi means. Phi contains two components, P restricted on E and mu P restricted on E. Because P is the probability measure, P restricted on E has total measure less than or equal to 1. And because mu PE is strictly larger than 1, mu P restricted on E has the total measure strictly larger than 1. So we have two measures defined over E, one with total measure less than or equal to 1, and another with measure strictly larger than 1. So there is a unique convex combination of the two measures, that is the probability measure. And the phi is precisely that probability measure. So to interpret, here the decision maker updates each prior P towards the contraction measure mu P. And that constitutes the posterior set of the decision maker. Let me give you a couple of examples so that you can be familiar with the contraction rule. First, consider this simple example. There are three states of the world, and the realized event has two states. The prior set is generated by the convex hull of P and P hat, where the distributions of P and P hat is given by this table. We first derive the contraction measure here. The contraction measure mu P takes the state-wise maximization, so it is given by this rule. And notice here that the contraction measure assigns the realized event a total measure that is equal to 0.8. So the situation belongs to the first case, where the realized event has small ambiguity. So the posterior set is a singleton, and the posterior is simply the normalization of the contraction measure on the realized event. So we have the posterior Q star to be like this. Next, we consider more complicated example. The setup is the same as before, but now we have different distributions for P and P hat. We again derive the contraction measure, and note here the contraction measure assigns a total measure 1.2 to the realized event. So it belongs to the second case where the ambiguity is large. And therefore, each prior is updated to a posterior following the function phi. We write down the restriction of the prior P here and the restriction of the contraction measure here. So the posterior is the unique convex combination of the two measures, that is the probability measure, which can be easily derived here. Again, we write down the posterior of P hat as Q hat here. So the contraction posterior set is generated by Q and Q hat, which is the convex hull of the two. Here is a graphic illustration of the two examples. Because there are three states of the world, we can use two-dimensional space to denote the set of all probability distributions. So this big triangle contains the set of all probability distributions, where x-axis denotes the probability of S1 and y-axis denotes the probability of S2. In the first example, the prior set is the line segment of P and P hat, and the contraction measure is within this big triangle, so it means the ambiguity of the realized event is small. and we update simply the contraction measure to the posterior by normalizing it. In the second example, the contraction measure is above the triangle. This corresponds to the case where the ambiguity of the realized event is large, and therefore we update each prior towards the contraction measure, and we have the posterior set to be the 9th segment between Q and Q hat. It might be a little bit confusing why 1 is a reasonable cutoff for determining whether the ambiguity of the realized event is large or not. Here is a justification. Suppose the state space takes the product form where D1 and D2 are a pair of relevant states and theta1, theta2 are signals. Consider two prior sets P1 and P2 where the priors distributions are given by the table. The realized event is D1, D2 product theta1. That is, theta1 is observed. We're trying to argue that P1 is updated to a singleton posterior set, and P2 here serves for a particular purpose. Let me start with P2. P2 is all ambiguous on D1 and D2. This is because P2 always assigns probability 0.4 to D1 and probability 0.6 to D2. And P2 agree with P1 on the realized event E. To see this, note that P1 and P2 assigns the same probability distributions on theta1, and P1 hat and P2 hat have the same probability distributions on theta1. So price set P1 and P2 agree on E. The first postulate says that information should not increase ambiguity, and therefore P2 should be updated to a singleton posterior set because it is all ambiguous on D1 and D2 in prior. The second postulate says that the posterior set should be a function of the prior distributions on the realized event and should be irrelevant with the prior distributions on the complement of the realized event. And by this postulate, P1 and P2 should be updated to the same posterior set because they agree on the realized event. So, P1 should be updated to a singleton posterior set. And here, the requirement that mu P1E is smaller or equal to 1 is a sufficient and necessary condition for us to construct such a set P2 so that we can apply those arguments we've used to argue that P1 to be updated to a singleton posterior set. And that's the justification for the cutoff. Next, we compare the contraction rule with the four-Bayesian and maximum likelihood rules. To start with, let me introduce the two rules. With the four-Bayesian rule, every prior is updated to its posterior following the Bayes rule. That is, every prior that assigns a positive probability to the realized event is updated to its conditional probability on the realized event E. Here, bar means the normalization of the measure. So P restricted on E bar is essentially the conditional probability of P on E. The maximum likelihood rule is a two-step rule. First, we select the priors that maximize the probability of the realized event. That is, priors that are most consistent with the information are selected. Then, we update those priors following the Bayes rule. Clearly, the maximum likelihood posterior set is a subset of the four-Bayesian posterior set. Here is a simple graphic comparison of the three updating rules. Again, we consider a state space that contains three states, and the realized event is S1 and S2. The prior set is the convex hull generated by P1, P2, and P3. Let's look at the four-Bayesian posterior set. On the four-Bayesian rule, every prior is updated to a posterior following the Bayes rule. That means we can simply connect the 0 with the prior, then extend the 9 until it intersects with the boundary. Therefore, the convex hull of Q1 hat and Q2 hat is the four-basin posterior set. For the maximum likelihood updating, we first select the prior that maximizes the probability of the realized event. Here, P2 is the unique prior that maximizes the probability of the realized event, and therefore, it is the only one that is updated. And the maximum likelihood posterior set is a singleton, Q2 hat in this case. So the maximum likelihood punishes less likely priors very harshly by directly ruling them out. However, this might create a problem. Here, P1 is also very likely given the information. However, all of a sudden, it is disregarded by the maximum likelihood rule. By comparison, the contraction rule and the four-basin rule update all priors in this case. However, the four-basin posterior set is oversensitive to less likely priors. Because every prior is updated using the base rule, less likely priors are amplified more, and they affect the four-basin posterior set more. And in this case, you can see that P3 is actually very unlikely given the information, but it determines one endpoint of the posterior set Q1 hat. The contraction rule does not have such problem. The reason is the following. So here P3 is a very unlikely prior, although it is updated to a posterior here. But the posterior, which is a convex combination of P3 and the contraction measure, actually gives a small weight to P3 because P3 is far away from the boundary. So that means with the contraction rule, although every prior is updated, but less likely priors are weighted less during the updating process. And that's basically the comparison of the three rules. Our discussions also have implications about the continuity of the three updating rules. First, four-basin rule is not upper hemi-continuous if the prior set contains a prior that assigns probability 0 to the realized event, because FB is very sensitive to less likely priors. The maximum likelihood updating rule is not lower hemi-continuous, because when there are multiple priors simultaneously maximizing the probability of the realized event, the ML posterior set is unstable. By contrast, the contraction rule is continuous in the following sense. For any sequence of prior sets Pn, if Pn converges to the prior set P in Hausdorff metric, then for any event E, we have the contraction posterior set by Pn converges to that by P. Next, we studied divisibility. There are a lot of situations when the decision maker needs to process multiple pieces of information. So in this case, the arrival order of those information might matter for the decision maker's final belief. An updating rule is said to be divisible if the posterior set is all affected by the order in which multiple pieces of information arrive. Cripps studies the problem of divisibility when there is no ambiguity. And in this paper, we show that the contraction rule is a divisible rule. And here is the proposition. For any two events F and E, the following two situations are equivalent. In the first situation, the decision maker observes the two pieces of information simultaneously and updates her belief for once. In the second situation, she first observes event E and updates her belief, then she observes event F and updates her belief again. The proposition says that the posterior sets of the decision maker in the two situations are identical. Although we state for two pieces of information, the proposition also holds for multiple pieces of information. So that means with the contraction rule, even if we don't know the order of arrival of multiple pieces of information, and we don't know the process of the decision maker processing those information, it is without loss of generality to assume that the decision maker aggregates all the information together and updates her belief only once. We provide a simple illustration for why the contraction rule is divisible. The reason is the contraction measure remains unchanged after updating. So here the prior set is the triangle, and the posterior set is given by the convex hull generated by Q1 and Q2. And note that the contraction measure remains unchanged before and after the information. So because every prior is updated towards the contraction measure, if it does not change, then the posterior set of the decision maker should not be changed by the order of information. Similarly, the four-basin rule is also divisible, and it has a similar geometric reason. With the four-basin rule, we can view 0 as the contraction point, because every prior is updated away from 0. Because 0 is always 0, the contraction point of the four-basin rule remains unchanged, and thus, the four-basin posterior set will not be changed by the order of information. Next, we are going to provide the axiomatic foundation for the contraction rule. Because we want to work with the choices of the decision maker instead of their beliefs, we introduce the axiomatic framework. An act is a function that maps each state of the world to a given payoff, and the calligraphic F denotes the set of all acts. An evaluation function characterizes the decision maker's choices by associating each act a value. The value is interpreted as the certainty equivalence of that act. And in particular, we require the evaluation function to admit a max-min representation, such that the evaluation of each act is equal to its minimized expected payoff over some convex and compact set of priors P. And in this case, we say P represents V. And by Gilbert and Schmiedler, each evaluation function can uniquely pin down the decision maker's belief set P. And therefore, by working with the set of all evaluation functions, we're essentially working with the set of all possible belief sets of the decision maker. Recall that an updating rule is a function that maps the decision maker's prior set P and realizes the event E to some posterior set. And parallelly, we can define an updating rule over evaluation functions. Here, V is the decision maker's ex ante evaluation function, and E is the realized event. The updating rule gamma updates the tuple to some ex post evaluation function of the decision maker, V E gamma. And V identifies the decision maker's prior set, and V E gamma identifies the decision maker's posterior set. And for simplicity, when gamma is clear, we write VE instead of VE gamma. Then, we can define an arbitrary updating rule in this new framework. Gamma is the contraction rule. If for any evaluation function V that is represented by P and any event E, the ex post evaluation function is represented by the contraction posterior set. And gamma is four-basin rule if for any V represented by P and any event E, the ex post evaluation function is represented by the four-basin posterior set. Now, I'm going to present the axiomatization foundation for the contraction rule. Throughout this process, I will usually start with an axiom that is too strong for the contraction rule to hold, but easy to interpret. Then, I will show how to derive a weaker version of that axiom so that the contraction rule can satisfy it. Let me start with the increased sensitivity after updating, ISU. It says the following. If we have two acts, F and G, such that G is better than F on state S, which is included in E, and equal to F on every other state of the world. Then, if we have the ex-ante evaluation of F equal to the ex-post evaluation of F, we must have the ex-post evaluation of G to be higher than the ex-ante evaluation of G. And here is the interpretation. The decision maker becomes more sensitive to payoff differences on state S if the new information does not rule out S. Note that F plays a benchmark rule here because its ex-ante evaluation equals its ex-post evaluation. The decision maker can perceive a difference between F and G, and in particular, after the information, the difference should be more salient, and therefore, the difference between the evaluations of F and G should be higher after the information than before. And this could be reflected by the fact that G's ex-post evaluation is higher than its ex-ante evaluation, because F is already a benchmark now. The axiom is also closely related to dynamic consistency, and here is a restatement of the axiom, which is essentially equivalent to the original statement. It says the following: if the two X satisfy the same condition as before, and now we have two payoffs, X and Y, such that the mixture of F and X is as good as the mixture of G and Y at the ex-ante stage, then we must have at the ex-post stage the mixture of G and Y is better than the mixture of F and X. Here is the justification. Since F is worse than G, in order for the mixture of F and X to be as good as the mixture of G and Y, we have to ensure that X to be higher than Y. And therefore, the mixture of F and X is better than the mixture of G and Y on the complement of E, because F agree with G on the complement of E. The realization of E rules out the states on which the mixture of F and X is better than the mixture of G and Y, and therefore, at ex-post stage, the mixture of G and Y should be better. And we can interpret this as a version of dynamic consistency with monotonicity. However, as shown by Hanani and Klebanov, dynamic consistency is hard to be sustained in a general belief updating framework with ambiguity. And similarly, axiom ISU cannot be satisfied by any updating rule with ambiguity. And here is an example, which is also a simple proof for this claim. Consider the prior set P, which is generated by P and P hat. The distributions of the two priors are given by the table, where both priors assign probability 0.1 to state S4, so S4 is unambiguous. Let the evaluation function V be represented by P. We also consider for X, and their payoffs are also given by the table. Here, X and Y are certain payoffs that we will specify later on. And note that F and F hat only differ on state S1, and G and G hat only differ on state S2. Here is the observation. The prior P hat is the one that minimizes the expected payoff of both F and F hat, because P hat assigns a very small probability to state S3, while F and F hat assigns a very large payoff to state S3. Therefore, the difference between the ex-ante evaluations of F hat and F is actually given by the probability of state S1 on the prior P hat, which is 0.7. And similarly, we can show that the difference between the ex-ante evaluations of G hat and G is actually given by the probability of state S2 on the prior P, which is 0.6. Next, assume that the realized event is E, and let VE be the exposure evaluation function of the decision maker updated from an arbitrary updating rule. It is represented by some posterior set Q. The only thing we know about Q is that it is supported in the realized event. Now we can suitably choose X and Y such that the ex-ante evaluation of F equal to the exposure evaluation of F, and so for G. The reason we can do so is because X and Y linearly affects the ex-ante evaluations of F and G, but they do not affect the exposure evaluations of F and G. By axiom ISU, we can have the following. The difference between the exposure evaluations of F hat and F should be weakly larger than their ex-ante difference, and so for G hat and G. Note that both F and F hat yields a higher payoff on state S1 than state S2. So their difference should be equal to the minimized exposure probability of state S1. And so for G and G hat. Now we have a contradiction because the summation of the minimized probability of state S1 plus the minimized probability of state S2 is strictly larger than 1, which is impossible. Here is a simple observation of the previous example. ISU is violated because the degree of ambiguity on the realized event is too large. Therefore, we should not anticipate that the ambiguity on the realized event to be resolved after the realization. And that's precisely what we are going to state. For this purpose, we need to define what we mean by ambiguous evaluation functions. An evaluation function V is ambiguous if we can find two acts, F and G, such that the mixture of F and G is strictly better than each one of them. This simply means that V is not linear and is represented by multiple priors. So there is ambiguity. And here is our axiom. Ambiguity-driven decrease the sensitivity after updating. It says that if we have F and G that violates axiom ISU, then it must mean the realized event has large ambiguity and is not resolved after realization. And therefore, the exposure evaluation function is also ambiguous. An equivalent statement of this axiom is that if we have the exposure evaluation function to be unambiguous, then axiom ISU must hold. We note that both Ford-Bayesian and the contraction rule satisfies this new axiom. In order to state the next axiom, we need to define some notations. We say E is V now if for any two acts, F and G, that only differ on E, we have VF equal to VG. That means the evaluation is independent with payoffs on event E. And equivalently, if E is V now, and we know that the prior set P represents V, we must have for every prior in the set P, it assigns probability 0 to E. We also define a mixture of two evaluation functions, which is given by the following. For any act F, its evaluation under the mixture is given by the mixture of its evaluations on the V and V hat. And we can easily show that this mixture is also an evaluation function. If P represents V and P hat represents V hat, we have the mixture is represented by the mixture of the two prior sets. Our next axiom is mixture independence, which says the following. If we have event E that is V hat now, but not V now, then the mixture of V and V hat should be updated to the same exposure evaluation function as V when E is realized. And here is the interpretation. Since E is V hat now, the only part of the mixture evaluation function that is relevant with E is by this alpha V. And therefore, V and the mixture evaluation function have the same ambiguity structure on E. The axiom simply says that if they have the same ambiguity structure on E, then they are updated to the same exposure evaluation function. The axiom is satisfied by four-Bayesian rule, but not satisfied by the contraction rule. Here is the reason. Because with the contraction rule, V and the mixture evaluation function might have different degrees of ambiguity on E. And we know for the contraction rule, the degree of ambiguity on E matters for the posterior set. And therefore, the mixture independence axiom is too strong for the contraction rule to satisfy it. However, we can weaken axiom mixture independence to the following one so that the contraction rule can satisfy it. The new axiom is called mixture independence without ambiguity. It says the following. If we have event E that is V hat now, but not V now, then if in addition V is updated to an unambiguous exposure evaluation function, we must have the mixture evaluation function and V are updated to the same exposure evaluation function. Here's the interpretation. Because V is updated to an unambiguous exposure evaluation function, it means that the ambiguity on E is already small. And therefore, in this case, only the structure of ambiguity determines the exposed evaluation function. And this axiom is satisfied by contraction rule and precisely captures the case when the ambiguity on the realized event is small. The next axiom is axiom betweenness. Let me start with introducing the act Fex. It denotes the act that equals F on E and yields a constant payoff on the complement of E. By considering Fex, we are actually considering the complement of E as a single state, and therefore we are ignoring the detailed probability distributions on the complement of E and focus ourselves on E. And here is the axiom. We consider two evaluation functions, V and V hat. The axiom says that if V hat is always in between V and its exposure evaluation function, then V and V hat are updated to the same exposure evaluation function when E is realized. We interpret this axiom as the one that characterizes all updating rules that preserve updating relevant components. For example, the four-Bayesian rule. Let me use the four-Bayesian rule to illustrate. Under the four-Bayesian rule, the posterior set is determined by the structure of ambiguity on the realized event. So the ambiguity structure on the realized event is the updating relevant component. Meanwhile, the four-Bayesian posterior set also preserves the ambiguity structure on the realized event because every prior is updated to a posterior. And thus, the four-Bayesian rule indeed preserves all updating relevant components. Back to the axiom. Since the updating rule preserves updating relevant components, we should have that V and VE share the same components on E. And because V hat is in between, so V hat also shares the same components. And as a result, V and V hat are updated to the same exposed evaluation function. The proposition here is a byproduct of our axiomatization exercise. It says that the four-Bayesian satisfies axiom mixture independence and axiom betweenness, and it can almost be characterized by the two axioms. That is, when the prior set does not contain any prior that assigns probability 0 to the realized event, then the four-Bayesian rule could be characterized by the two axioms. Again, axiom betweenness is too strong for the contraction rule to hold. Here is the reason. With the contraction rule, When the ambiguity on the realized event is small, the realization of it might completely resolve the ambiguity, and therefore, the contraction rule might not preserve the ambiguity structure on the realized event. That means, updating relevant components are not always preserved by the contraction rule. However, when the ambiguity is not resolved, the contraction rule does preserve the ambiguity structure because every prior is updated to some posterior. And in this case, the contraction rule does preserve updating relevant components. And because of it, we give the following definition. For a given updating rule, we say that E does not resolve ambiguity of V if the ex poster evaluation function of V is ambiguous. And we also give the definition for E does not strongly resolve ambiguity, which can be considered as the limiting case of does not resolve ambiguity. The definition of strongly resolve ambiguity is for technical purpose and would be used for the next axiom, which is a modified version of the betweenness axiom and is satisfied by the contraction rule. Here is the axiom, mixture ambiguity betweenness. It says the following. Consider event E that is V tilde now, and consider two evaluation functions. One is the mixture of V and V tilde. Another is the mixture of V hat and V tilde. Suppose that E does not strongly resolve ambiguity of W. Then the betweenness condition holds for W and W hat, implies that the ex poster evaluation function of V and V hat to be the same. Here is the interpretation. The condition that E does not strongly resolve ambiguity of W plus the betweenness condition imply that W and W hat share the same updating relevant components on E. And because W and W hat are both mixture of some evaluation function with V tilde with the same mixture ratio, it essentially means that V and V hat share the same updating relevant components on E, and therefore they are updated to the same exposed evaluation function. Axiom MAB can be implied by axiom mixture independence and axiom betweenness, and it precisely corresponds to the situation of the contraction rule when the ambiguity on the realized event is not resolved. The next axiom is very easy to interpret. It is called independence of irrelevant states, which says that if we have two evaluation functions that completely agree on E, then they should be updated to the same exposed evaluation function. The axiom is actually a weakening version of axiom betweenness and is satisfied by both four-Bayesian rule and contraction rule. In fact, this axiom is also satisfied by the maximum likelihood rule. So far, we have introduced the four axioms for contraction rule, and all of them are satisfied by the four-Bayesian rule. The final axiom is the only one that is satisfied by the contraction rule, but not by the four-Bayesian rule. V is ambiguous with respect to the partition if we can find two acts, F and G, such that the mixture of F and G is strictly better than each one of them. This simply means that V is not linear with respect to the partition. Here is the axiom, no more ambiguity by information. Consider an evaluation function V that is not ambiguous with respect to the partition, and consider an event that intersects each block of the partition at most one state of the world. Then, the ex poster evaluation function is not ambiguous. Here is the interpretation. Each block can be considered as a pair of relevant state, and E can be considered as a signal. And at the ex ante stage, the decision maker perceives no ambiguity from the pair of relevant states. So, at the ex post stage, she should not perceive any ambiguity from the pair of relevant states, because information does not bring ambiguity. Here is our main theorem. An updating rule is a contraction rule if and only if it satisfies axiom ambiguity-driven decreased sensitivity after updating, which is a weaker version of ISU. Mixture independence without ambiguity, which is the weaker version of mixture independence. Mixture ambiguity betweenness, which modifies from axiom betweenness. Independence of irrelevant states, and no more ambiguity by information, which is the only axiom that is violated by four-Bayesian rule. The next thing we're going to discuss is belief dilation, which is our major motivation. It is found that both four-Bayesian and maximum likelihood may lead to belief dilation, and Shishkin and Otrlaver precisely test this hypothesis and find that ambiguous information will typically not lead to belief dilation for ambiguity-averse decision makers. So to start with, let me introduce the framework and introduce what we mean by dilation. Let the state space be a product space where D denotes the pair of relevant states and theta is the signal space. Assume that there is a set of priors P. We say a signal dilates the belief set of the decision maker over the pair of relevant states on the updating rule Q if the marginal distributions of the prior set on D is a strict subset of the posterior distributions on D. Here, our definition of dilation is a weaker version of that of Wasserman and Cadane, because in their version, dilation means that every signal theta dilates the belief set of the decision maker, while we only consider one particular signal. So our version is a weak one. Let me first illustrate how four-Bayesian rule or maximum likelihood rule dilates the belief set of the decision maker using our motivating example. Here, the pair of relevant states are the price trend of the stock. D1 denotes that the price of the stock will go up, and D2 denotes that the price of the stock would go down. Theta 1 and theta 2 are suggestions of the expert. Theta 1 means that expert suggests that the price would go up, and theta 2 means the suggestion is price will go down. And we assume that the expert tells the truth with probability ranges from 0.2 to 0.8. So, the prior set is given by the convex Hall generated by P and P hat. P denotes the case where the expert is telling the truth with probability 0.8, and P hat corresponds to the case where the expert tells the truth with probability 0.2. Note here that at the ex ante stage, there's no ambiguity on the pair of relevant state because both P and P hat assigns probability half to D1 and probability half to D2. Now, let's consider what happens if some signal is observed. Suppose the signal is theta 1. Then with the four-Bayesian rule, we simply update each prior to its posterior following the base rule. That means P is updated to Q, and P hat is updated to Q hat. And for the maximum likelihood rule, we need to first determine what priors that maximize the probability of the realized event. And an interesting observation in this case is that both priors maximize the probability of theta 1 because both P and P hat give theta 1 a probability half. So, the maximum likelihood rule updates all priors and delivers the same posterior set as the 4 Bayesian rule. So, the convex hull of Q and Q hat is the 4 Bayesian posterior set as well as the maximum likelihood posterior set in this example. And clearly, there is ambiguity over the pair of relevant states after theta 1 is realized under the two updating rules. That is, the two updating rules dilate the belief set of the decision maker. In contrast, the contraction rule does not dilate the decision maker's belief in this case. We first write down the contraction measure. And note that the contraction measure assigns the realized event a measure that is equal to 0.8, which is strictly smaller than 1. So the posterior set is a singleton, and the posterior is simply a normalization of the contraction measure on the realized event. Clearly, the posterior assigns each pair of relevant states a half probability. Here is our proposition, which states that with the contraction rule under generic conditions, any signal will not dilate the decision maker's beliefs over pair of relevant states. The conditions are either the prior distributions on the pair of relevant states is a singleton, or there are two pair of relevant states, or the prior set is entirely contained in the interior of the probability space. Under either one of those conditions, then no signal will dilate the decision maker's pair of relevant belief set. Beyond the non-dilation results, we also have other results in the paper. We summarize the results here. First, contraction rule predicts underreaction to ambiguous information. This is a new finding by Liang 2021. The contraction rule also predicts learning with a sequence of independent, ambiguous, and informative signals. And finally, we apply the contraction rule to ambiguous information design in an earlier version of the current paper. And we find that if an agent updates with the contraction rule, then the principal can design suitable ambiguous information structures to almost fully extract the surplus of the agent.